Okay, it is now 6:01, so let's go ahead and get started. I'm assuming everyone can hear me. Can someone in chat just let me know whether you can hear me or not? Okay, wonderful. Thank you all very much. All right, so let's go ahead and get started. So once again, welcome to MBA 501. So today we are going to cover t-test and ANOVA. Last class we covered partial correlation and regression. So now we're going to move on to a very different topic in t-test and ANOVA. It might be easier in some ways. If you were struggling a little bit with correlation and regression, that's okay. These inferential statistics, even though they cover some of the same concepts, they are different. So if you're struggling with the prior stuff, then maybe this stuff will be easier to you. Maybe this stuff will be easier to work with. So, and as you see today, we're going to cover a 1 sample t-test, a 2 sample t-test, and ANOVA. So we're going to cover all 3 topics. Once again, we're having to scrunch topics together because we missed that one class, but it shouldn't be too much because all these analyses are fairly similar. One quick note before I get started, and this is something I apparently didn't make clear enough, so I apologize for that. In the first half of every class, I provide a conceptual review or conceptual information about a new inferential statistic. So if you remember from last class, the stuff I lecture about is the inferential statistic and how it works conceptually, how it works theoretically. And in the second half of the class, you're supposed to use the guides and you're supposed to actually perform the statistic. I've had a few emails where someone said, where a student has said something like, I opened up the guide, it was talking about regression. I don't know what that is. Where can I go to learn more about regression? And the answer is the lecture. The lecture was about regression. So therefore, if you're opening the guides and these terms aren't familiar to you, you probably need to go back and rewatch the video or maybe just make that connection. I think I had one student send me an email that said, I noticed that in your lecture you talked about regression. I noticed in the guide it talks about regression. Are those the same thing or are they completely different? And the answer is yes, they're the same thing. So just be aware of that. And I apologize for not making that more clear before. Also, another quick note is, as always, you have the guides from when I taught this MBA class online a year or 2 ago. Also, this material is starting to overlap more with the undergrad stats class I teach. In undergrad stats, I do teach inferential statistics. That's stats part 2 for the undergrads. So if this is also really confusing to you, go to my YouTube channel that I upload all of these lecture videos to, and that YouTube channel also has my undergrad videos. So take a look at those. Maybe the way I explain this to undergrads might be a little bit easier to understand, and then you can transfer into listening to these MBA level lectures that, yeah, they're hard, they're difficult. I'll admit that. These are hard concepts. So maybe starting with listening to it in the undergrad lectures and then listening to it again in the grad level lectures, that might help you out. But that's all I have to note about class related things. Does anyone have any questions or comments about anything? Okay. So yeah, and if anyone has any questions, feel free to send me a message as class is winding down, and I'm always available to answer questions after the lecture. So just shoot me a message, just say, hey, Dr. Howard, can we talk after class? And I'm more than happy to do that. Okay, so to start class today, we are going to talk about 1 sample t-tests, 1 sample t-tests. And to start, we're gonna go back to the same exact chart we've looked at several times now. And before we were talking about the relationship between variables. And if you remember, gosh, how long has it been now? A week ago, I guess, 2 weeks ago, week and a half, whatever. We talked about the relationship between variables. And we talked about when there's only 2 variables, that's when you're looking at correlation. We then on Monday talked about how we're looking at the relationship between variables. And when we have 2, but we're controlling for others, we're looking at partial correlation. We also talked about on Monday when you're studying the relationship between variables and you have many predictors in one outcome, that's when you're going to be using regression. And then I didn't mention this, but just so you're aware, there are analyses that look at many predictors, many outcomes, structural equation modeling being one of them. And you can use these other analyses to look at many predictors and many outcomes. We're not going to be covering those other analyses in this class. That's something you would cover in our PhD program, for instance, but they do exist. So if there's ever a time you're in a practical situation where you say, hey, I know I have a lot of predictors, I know I have a lot of outcomes, what analysis would I use? Be aware that analyses do exist to investigate those type of research questions. And if you need help, feel free to email me. Even after you're done with this class, feel free to email me about any stats question you have, and I can possibly direct you to the best analysis to use. Like I said, for instance, one of those analyses might be structural equation modeling that we teach at the PhD level in this program. Okay, so with that noted, we're going to shift gears now. Today's lecture is going to completely shift gears, and instead of looking at the relationship between variables, we're now going to look at analyses that investigate the difference between groups. So we're taking a break from looking at the relationship between variables. We will come back to them, so don't forget all about them. But now we're going to look at the difference between groups. So therefore, when you're explaining the difference between groups, the first question you should ask yourself is, how is your outcome gauged? How is your outcome measured? So the two possibilities for that we'll cover in this class are, you're either looking at the number of members in the groups, or you're looking at a separate measured variable. So in this instance, you're looking at something like the differences between groups. Groups might be classrooms, might be factories, might be countries, might be states, any type of way you could group people, that could be your grouping variable. But your outcome is something else you've measured. Your outcome is something else you've measured. So for the classroom example, that might be test scores. For the state example, that might be average company revenue of the states. For the factory example, that might be average employee job satisfaction. So in each of those examples, we have a grouping variable, such as classroom, state, or factory, but we also have a separate measured outcome, such as test score, revenue, or average job satisfaction. So therefore, what we're going to cover today are analyses that both look at the difference between groups, and also they have an outcome that's a separate measured variable, that they have something in addition to the grouping variable as their outcome. And then as you'll see, the next thing you should ask yourself, if this is the case for your research question, is how many groups do you have? How many groups are you looking at? So if you know you're looking at the difference between groups, if you know your outcome is gauged as a separate measured variable, you should then ask yourself, how many groups do you have? How many groups are you interested in? And today we're going to cover, and we're going to start with when you just have one group. When somehow you're interested in looking at the difference between groups, and I know that sounds counterintuitive, but hopefully that will make sense in a second. But it's when you're looking at the difference between groups, you have a separate measured outcome variable, and you're looking at only one group is where we're going to start today. And that analysis would be a one sample t-test. That analysis is going to be a one sample t-test. So a one sample t-test is when you're somehow looking at the differences between groups, in this case just one group, and you have a separate measured outcome variable, and you're wanting to assess how that group differs from something on that separate measured outcome variable. So, and I know the one group example sounds counterintuitive at first, but it will hopefully make sense in a few slides. Okay, so let me clear this. Okay, and that's all of what I just said. And we're going to start with the one sample t-test. So this is what a one sample t-test does. A one sample t-test analyzes the difference between a sample mean and a given value. So in this case, we have a group, we have a measured outcome variable, and we're interested in seeing whether that sample mean, whether the mean of that group on whatever you measured is different than a given value, and you provide that given value. That given value is something that you select. So here is a visual demonstration of it on the next slide. So this is what a one sample t-test looks conceptually if we were to visualize it. As you see, this is our group right here. So we have a group, and in this example, they have a normal distribution. So it looks something like a bell curve, and we have a mean for that group. And we could use a one sample t-test to see, well, does this mean of our group, does that differ from a chosen value? Does that differ from a chosen value? So one example might be, let's go back to the simple example of a classroom and we have test scores. So we might be interested in, well, does the average test score of this class differ from a value of 80? So does the average value of test scores for this class, that would be represented right here, average value of test scores for this class, does that differ from a value of 80? And the value of 80 might fall somewhere like right here on the distribution. And if that was your research question, you should automatically, moving forward, know that we should use a one sample t-test. A one sample t-test would answer this question of does our average test score, because it's one group, one sample, does our average test score for this one group, this one sample, this one classroom differ from a value we choose? And that's when we would use a one sample t-test. Okay, and this would also hold true for the other examples I gave. We might have a sample of states, for example. We might have the average revenue of each state, or the average revenue of these states. So we might have that as a sample. We might make a distribution of that. And we could select a certain value, whether it's 1 billion, 2 billion, whatever number would make sense, and see if the average revenue of the companies in the states differ from that chosen value, And then the last example that I mentioned before might be we're looking at a sample of employees that work at a factory. So we have one factory, we're looking at a sample of employees for that one factory. We might want to see, does the average employee job satisfaction, so once again, average represented right here, differ from a chosen value? So if we're using a Likert scale, for example, we might say the Likert scale goes from 1 to 7, and 4 is right in the middle. So we might want to test and see, well, does employee job satisfaction differ from a value of 4? Are our employees statistically significantly above that midpoint of 4? And we could test that with a one sample t-test. That would be quite easy to do. Okay. So clearing that. So when performing a one sample t-test, our null and alternative hypotheses are usually, so the null is usually that there's no difference between the mean and the selected value. So that would be the null hypothesis, the thing we're trying to reject, that there's no difference. And then our hypothesis is that there is a difference between the mean and the selected value. So we're typically going to hypothesize that our group, our sample that we're looking at, the mean of that sample is statistically significantly different than that chosen value. So whether it's a group of students in a class with average test scores, we would typically hypothesize that their average test scores is different than that value that we choose. So therefore, the implied null is that there's no difference. The implied null is that the average values of that classroom is not statistically significantly different than that value that you chose. And we're trying to reject that. We're trying to reject that there's no difference between the chosen value and the mean of the classroom. So therefore, when we run a one sample t-test, we're going to get a p-value. If we get a p-value of less than 0.05, we can reject that null. If we get a p-value of less than 0.05, we can reject that there's no difference if we have a p of less than 0.05. So therefore, if we reject the null, we can then go with our hypothesis, also called the alternative hypothesis. And if we can reject the null if there's no difference by getting a p less than 0.05, then we find support for our hypothesis. We find support that there is a difference between our mean of our group and that value that we chose. Okay. And I already went over these when we were looking at the picture, but here's some examples, and here's some other examples that if you want to review, you can go back through the PowerPoint and look at it yourself. So the first one is exactly what I said before. You could also, in the second one, ask something like, is the class's average height significantly different than 5 foot 5 inches? You could test that with a one sample t-test because you have a chosen value, 5 foot 5 inches. You have a sample, the class, and you can assess whether the class's mean is different than that value that you chose. And then also you could have a company's yearly revenue. You could get their yearly revenue for however many years, 20, 30, maybe 100. And you can see whether their average yearly revenue is significantly different than $10 million. So once again, in this example, we have a sample of all the yearly revenue for that one company. So it might be 100 observations. And we can test whether the average of those 100 observations is significantly different than 10 million. We can once again do that with a one sample t-test. All right, so one question you might have is what goes into whether a group is significantly different than a certain value? So what goes into determining whether your one sample t-test is statistically significant? And there's 3 factors. And that's the mean, the variance, and the sample size. So once again, I'm going to draw the chart we looked at before, or the figure we looked at before. So we might have a selected value. And the first of these is pretty simple. The first of these is the mean. And as you probably would have already guessed, if we have a mean that is close to that selected value, then it's going to be much less likely that our results are significant. If we have a mean that's close to that selected value, it's going to be much less likely that our results are significant. Because for our results to be significant, there needs to be a difference. If there's not much of a difference, it's going to be hard to find significance. On the other hand, if we have a mean that's far away, like over here, then it's going to be much easier to find statistical significance. It's going to be much easier to find statistical significance because our mean is really far apart. Our mean is really far away from that chosen value. And once again, we want it to be significantly different from that chosen value for us to find statistical significance. Okay, the next one is variance. And variance is represented by how wide our distribution is. If you remember from our measures of variance, like variance and standard deviation. So if we have a sample where the variance is really wide, something like this, it's going to be really hard to find statistical significance because our variance is so wide, so much of our population is distributed, it'll be much easier to say, well, this value is a plausible explanation for the mean. It would be much easier to say that this value is a plausible explanation for the mean if our variance is really wide, because that value falls relatively in a relatively normal expectation for our distribution. If our distribution is wide, it's much harder to say that that's not the mean. On the other hand, if our sample is really narrow, if our distribution is really narrow, where almost all the observations fall right around the mean, then it's going to be much easier to find statistical significance. It'll be much easier to find statistical significance because all the values are bunched together, and it'll be much easier to have a selected value that's far away from those values. It'll be much easier to have a selected value that's far away from those values. So therefore, if your mean is far apart, you're going to be more likely to find statistical significance. If your variance is really narrow, it'll be much easier to find statistical significance. And the last part is sample size. And you could think of sample size of all the observations that go underneath these distributions. So all the little dots that make up this distribution. And you might have a sample size that's relatively sparse, like the red dots. We don't have many participants. Or you may have a distribution that has a lot of observations, like the green dots. And if the more observations you have, the easier it is to find statistical significance. And that goes for any statistical analysis. If we have more observations, it's going to be much easier to find statistical significance. I think we've talked about this before, but I'll talk about it now just in case we haven't. Is that's also one of the concerns with just any statistic, is because our sample size affects whether our results are statistically significant, and you could always just get a larger sample size to make sure your results will be significant. Then once you start getting sample sizes of 1 million participants, I mean, sometimes even lower, sometimes 10,000, 100,000, and then definitely once you get to 1 million, your results can be very, very small and still be statistically significant. And that is something that is concerning about statistics itself, is once you get a large enough sample size, then almost everything will be statistically significant. And that goes into what we talked about before the midterm, about the difference between practical significance and statistical significance. So that's something always important to keep in mind with inferential statistics. Okay, so those are the three things that go into whether a group is significantly different than a certain value, and that was mean, variance, and sample size. Okay, so a question you might have, is when would we ever use this? When would we ever use a one sample t-test? And I'll be 100% honest, in research and in business, we're probably not going to use it that often. We're probably not going to use a one sample t-test all that often. Can anyone guess why this analysis might not be that common? Any guesses why this analysis might not be that common? Okay, yeah, so one person says it doesn't tell you that much information, and that's a good answer. I like that. Yeah, one sample t-test doesn't tell you that much information, particularly because there's not that many instances that we absolutely know for sure a certain value that we're interested in. There's not that many cases that we're going to say, oh, an employee's job satisfaction of 4 is really, really important. Or a class's test score, as long as it's different than 70, we'll be happy. There's not that many instances that's going to occur. More often, we're interested in comparing the differences between groups rather than having a selected absolute value that we know is important. Because there's not that many cases that we have a black and white value like that, that we know that, hey, anything below this value we don't care about, anything above it we do, so we need to test this one value. We don't come across that often. So therefore, one sample t-test, you're probably not going to use it too much. However, there are some instances it could come into play, and that's why you should know it. And as I said, one of those instances is if you know a predefined value is important. So if you know that For example, with MBA program accreditation, maybe we want to make sure that our MBA incoming classes have standardized test scores that are above a certain value, and we need to be absolutely certain we exceed that absolute value. We could run a one sample t-test on it. If our accreditation bodies say that, hey, your students have to have average standardized test scores above this value, we can do a one sample t-test to make sure our students are indeed significantly above that value. Another example is when you have a certain expected value for a sample. So if I'm conducting a research study and I know that in a population I'm testing, the average age is about 35, I might want to go ahead and collect my sample and then do a one sample t-test comparing my new sample to a number of 35 in regards to age. I might do that just to make sure that, hey, I didn't get a weird sample, I didn't get a fluke. So therefore I would collect my new sample, compare it to an average age of 35, a value of 35, and then if it's not significant, then I would be happy about that, because that would insinuate that my sample is pretty typical. But if I were to collect that sample, compare it to an average age of 35, and it is significant, then I might be concerned, because that would insinuate that I collected a sample that might not be representative, or at least is not consistent with my prior samples. So therefore, a one sample t-test could be useful in that instance. Okay. And then last, I have two more. The next one was if you have some type of common sense value. This is pretty rare, but it could happen. If you have some type of common sense value where something like, gosh, I can't really think of a good example for that, but there might be instances you might have a common sense value that you just know you want scores above that. This doesn't quite work, but if you know that a failing grade is a 60, you might just want to make sure that your class does above a 60 as their average test scores, so they're significantly different than a failing grade. That's not a great example, but y'all get the point. And then the last one might be if you're performing a replication study. So in research, there might be a certain phenomenon that exists that we know that, hey, on average, we get a correlation of 0.2. I guess a correlation wouldn't work, but we get a mean value of 20 whenever we conduct this study. And whenever we bring people into a lab, whenever we get them to do a certain thing, on average, people score a 20. So therefore, if we're trying to replicate that effect, we might want to first show that, hey, we brought people into a lab, and they indeed were not significantly different than a value of 20, that they are similar to a value of 20. So therefore, that gives you assurance that you were able to successfully replicate the prior result, or you're able to successfully replicate what is typically found in that context. So those are 4 instances you might want to use a one sample t-test. It doesn't come up as often you would think, but another reason why we should learn it is because a one sample t-test is extremely similar to a 2 sample t-test. And a lot of the logic that goes into a one sample t-test is the logic that's used for a 2 sample t-test. And as we'll find out later today, the logic for a 2 sample t-test is also very similar to ANOVA. So all this that we're learning today builds on top of each other. So you should be able to conceptually understand a one sample t-test, because that makes the other parts much easier. Okay. Also, this is just another side note, is we almost always apply a one sample t-test on measured variables that have clear established meanings. So things like height, weight, money. Also, when I said standardized test scores, I mean standardized tests. So it's tests that have standard values that we interpret in a very meaningful way, that might have clear cutoffs, that might have clear ranges, that might have established percentiles. Those would also be instances we might want to use a one sample t-test. It's much less likely we would perform a one sample t-test on a Likert scale, because if you have, 1 strongly disagree, 2 disagree, 3 slightly disagree, those things have a little bit less meaning. Even though we have words associated with those values, it might be unclear exactly how our sample distribution falls on 1 through 7 for a Likert scale, especially if we don't have ample prior research, especially if it's a scale that hasn't been used that often. So therefore, we might not use a one sample t-test as frequently with a Likert scale as we would with either height, weight, money, or a standardized test score. Okay, so that is all for one sample t-test. That's pretty straightforward. Are there any questions about a one sample t-test before we move on to a 2 sample t-test? Does the T stand for anything? That is a good question. That is a really good question. I will have to double check that. I want to say no. My first instinct is no, because there's a t statistic, and it's part of the t distribution. So my first instinct is to say no, the t doesn't stand for anything, but I will be sure to double check that. So very good question. Are there any other questions or comments? Okay. If there's no other questions, then we will move on to a two-sample t-test. A two-sample t-test. So what is a two-sample t-test? And as you can guess, a two-sample t-test is used to determine whether two sets of data are significantly different from each other in this instance in regards to their means. And that's what I have in the next bullet point, is a two-sample t-test is used to test whether the means of a measured variable in two groups is significantly different. So in this example, we're going to have two groups, and it has to be exactly two groups. And we're going to have a measured variable for both of the groups. It's going to be the same variable. So this might be we have two different classes, and they both took the exact same test. And that's very important, that to perform a two-sample t-test, the measure has to be consistent across the both groups. You can't have something like comparing job satisfaction in group A with job performance in group B using a two-sample t-test. That just doesn't make sense. It has to be the same outcome variable in both the groups. So in this case, you would use a two-sample t-test to compare the means of group A and group B in regards to their job satisfaction on a common measure, or in regards to their job performance on a common measure. So we have a grouping variable, so it might be classes, for example, class A and class B, and we have an outcome variable that's common among the two groups, such as test scores on the same test. Okay, so once again, two-sample t-test used to test whether the means of a measured variable in two groups is significantly different. Okay, so some examples. We might ask ourselves in our sample, do women have better test grades than men? So in this example, we would have, we might collect test scores in a class. Let's say in our class, we have 60 students. Let's say we might have 30 women and 30 men. And we could test by a two-sample t-test that on our test, did women score significantly better than men on that test that we gave to our class of 60 students with 30 men and 30 women. Another example might be, are men taller than women? So once again, we could take our class, we could measure everyone's height, and then we could assess on average, does the average mean of the men differ from the average mean of the women in regards to their height? So we can empirically assess via a two-sample t-test, are men indeed taller than women using our sample of our students? Okay. Another example, in sticking with classrooms, so we could have a class taught by Dr. Howard. We could have a class taught by Dr. Smith. We can give those two classes the exact same test. And then we could assess whether people in the class taught by Dr. Howard on average performed better than the class taught by Dr. Smith in regards to their test scores. Okay. And then the last example I'll give you is you might have two different training groups. You might have training group A that went through an existing training, our old training program, but then you might have training group B that went through a new training program. So maybe training group A watched a video, whereas training group V used a virtual reality headset and got to do a really cool training. And then you could see, you could then measure their job performance after the training. So maybe a month later, we would go and we observe employees in group A and employees in group B on the job and assess their performance. And then we could test via a two-sample t-test. Did the employees who went through training group B on average have better performance than those in training group A? I think I said that correctly. So we could see whether there is a mean difference between the means of group A and the means of group B, because this is all about, two-sample t-test is all about comparing mean differences, comparing the means of two groups. So therefore we could assess whether on average group A had a higher mean than group B, or we can compare the means of the two groups is another way to word it. Okay, so in performing a two-sample t-test, our null and alternative hypotheses are usually, so our null is usually that there's no difference in the means of the two groups. So the null is usually there's no difference in the means of the two groups. And our hypothesis, also called the alternative hypothesis, is there is a difference in the mean of the two groups. So once again, we would collect our data, we would get our samples, we would give the test, we would collect our data, and then we could try to assess whether there is a significant difference in the means of those two groups. And once again, as always, if we get a p-value of less than 0.05, we can reject the null. If we collect our data, we compare the means via a two-sample t-test. If we get a p-value of less than 0.05, we can reject that null. So we can reject that there would be no difference in the means of the two groups, which would provide support for our hypothesis that there is a difference in the mean of the two groups. So once again, if we get a p of less than 0.05, we can reject that there's no difference, and that gives support for our hypothesis that there is a difference in the mean of the two groups. Okay. And this is a visual representation of what a two-sample t-test looks like. So in this example, we have group A, we have group B, and just like before with the visual representation we looked at before, these groups have a mean, and these groups have variance, as we can see in their distributions. So what a two-sample t-test does is it assesses whether these means are statistically significantly different, whether there is a statistically significant difference in these two means. And without knowing anything else, if y'all had to guess right now, would y'all expect these two means to be statistically significantly different? Would you expect these two means to be statistically significantly different? What do y'all think? Would these be statistically different? Okay, so one person said no, that the means would not be different. Any other guesses? Okay, another person said no, one person says yes. All right, so we have 3 no's, we have 1 yes, and we have a we don't know. I'll say that we don't know, I can accept that, we don't know. Because we don't know what the exact numbers are behind this data. This is just a visual representation, so you cannot say with certainty. But I would also accept, and the answer I was actually looking for is yes, we probably could expect these to be different, because we can see that their means are quite different, their means are quite far apart, but also just as importantly, their distributions are very different. Their distributions are very spread apart, but almost none of the observations for group A overlap with the observations for group B. And that would insinuate that their means are probably significantly different because virtually none of their observations overlap. These two distributions are almost entirely different. So therefore, we would probably expect these means to be statistically significantly different because they're far apart and their distributions overlap hardly at all, that there's almost no overlap in their distributions. So we probably would expect these differences to be statistically significant. All right, but here's another example. In this example, we have a blue group, we have a red group. We plot them visually, and this might be what it looks like. Would we expect these two groups? Yeah, so, and this hopefully answers your question. So would we expect these two groups to be statistically significantly different, especially compared to the last one? So would we expect these two groups to be statistically significantly different? What do y'all think? Exactly. This would be much less likely to be statistically significantly different because as we see, their means are closer together, their means are much closer together, but also their distributions overlap a significant amount. There's quite a bit of overlap here because we see with the red group, their distribution is right here, whereas with the blue group, their distribution is right here. But there is a good amount of overlap between these two groups. So therefore, we would probably assume that there would be a small chance of getting statistical significance when comparing the means between these two groups. Not to say it's not impossible because their sample size could be huge. These could be 10 million observations. And if that was the case, then yeah, you might find statistical significance if there's 10 million observations. However, it's pretty reasonable to assume that these two groups would not have a statistically significant difference in regards to their means, that this is probably not statistically significant. So therefore, I hope that answers the question. Is it because in the prior example, they're not on top of each other and actually separate? The answer is yes. The answer is yes. That in the prior example, it looked like this. Those distributions were quite distinct. The means were far apart. Their observations did not really overlap. Whereas in this example, their means were much closer together and their observations overlapped quite a bit. So it'd probably be pretty difficult to find a statistically significant difference in regards to their means. However, as one student noted, we don't know that for sure. We cannot determine that just from looking at the pictures, and that's all we need to actually perform a two-sample t-test, because a two-sample t-test will give you a indicator of whether those means are statistically significantly different. Okay. And this also answers that question even further. What goes into whether the two groups are significantly differ? And what we just established was it's their mean, their variance, and their sample size. So once again, if their means are far apart, that's much easier to find statistical significance as opposed to when their means are close together. Also in regards to variance, if the distributions are really tight, if the distributions are really compact, and there's hardly any overlap among their distributions, as you see in the blue distributions, and that also would be very likely to be statistically significant because not only are their means far apart, but their distributions are very tight. There's not that much overlap. However, if they have wide distributions, as you'll see in the red examples, if they have wide distributions, and this is supposed to be two separate distributions, and I kind of messed up where their mean should be, but we'll ignore that. Actually, I'll see if I can fix it real quick. Eraser, erase that. Okay, so now their means, because I'm a bad drawer, probably would look something more like that. So as you can see in this example, their means are much closer together than the blue distributions, and also their distributions are much wider than the blue distributions. So in this example, it would be much harder to find statistical significance because there's so much overlap in these distributions. It would be very hard to argue that these means are statistically significantly different because there's so much overlap in those distributions and the means are closer together. And then the last part, as we just talked about, if your sample size is large, that's going to be much easier to find statistical significance. So if these blue distributions have a sample size of 1 million, that's going to be pretty easy to find statistical significance. Whereas if these red distributions have sample sizes of 30, that's going to be much harder to find statistical significance. It wouldn't be impossible, it would just be much harder. Clear all that? Okay. So when would we use this? And honestly, we would use a two-sample t-test quite often, both in research and in practice. There are a lot of instances we would want to use a two-sample t-test. And these instances would be is when we're looking at the differences between training groups. I use it all the time to compare training groups. It's very common for companies when they implement a new training to give the old training to one group of employees and then to give the new training to a different group of employees. And then you could compare, well, do the employees who went through the new training, are they actually significantly better than the employees that went through the old training? That's very common. We see that all the time. And that can give you assurance that, hey, we should use the new training. The new training is better than the old training, so let's start using it going forward. Also, I'll say that it's very common to do that, even if you might have two new trainings. If you know your old training sucks and you know for sure you need a new training, companies might make two new trainings. They might make a cheap one and an expensive one. They might make a training that's very cheap to use, and they might make a training that's very expensive to use. And then you might give those two trainings, both new ones, to all your employees. Well, you would take your two new trainings, and for one half of your employees, you give new training A. For the other half, you give new training B. And then you compare the two new trainings because you're trying to do a cost benefits analysis. You're trying to see, well, if they are equally effective, we should use the cheaper training. However, if the more expensive one is statistically significantly better, then we should probably consider the more expensive one. Even though it's more expensive, it is indeed better. So therefore, we use two-sample t-test all the time when comparing training groups. It's also very common when you're comparing work units. So if you're working for a company and you might have in your factory work unit A and work unit B, and you're trying to see, well, does work unit A perform better? Does work unit B perform better? You could do that. It might also be a question of which supervisor is better. Then if you're trying to compare two supervisors and you're unsure whether supervisor A or supervisor B is doing better, you could assess the performance of each of their subordinates. And you could say, well, supervisor A looks over these 30 people. Let's assess the performance of those 30 people. And supervisor B looks over these 30 people. So then you assess the performance of those other 30 employees. And then you could do a two-sample t-test to compare the performance of the employees or the subordinates under group A or under supervisor A, and compare that to the performance of the 30 subordinates to supervisor B. And then based on that, you could see or get at least some type of rough estimate. Are the employees under supervisor A indeed doing better than the employees under supervisor B? And you can assess that through a two-sample t-test. We might also have geographic regions. So if we want to see whether factories located in Alabama perform better than factories located in Mississippi, we could perform a two-sample t-test and see if on average, factories located in Alabama are indeed performing better than factories located in Mississippi. So in short, in case you haven't picked up on this, anytime you would make a bar chart with two bars, that's an instance you could apply a two-sample t-test. So anytime you think that your data would be best visualized by a bar chart with two bars, so such as this might be a bar chart comparing training group A versus training group B. If you ever think a bar chart with two bars would be the best way to visualize your data, then that would be a case you could use a two-sample t-test. That would certainly be a case you could use a two-sample t-test. Once again, if this was work unit A versus work unit B, and you think you could compare them visually by making a bar chart with two bars, so this might be the mean performance of work unit A and the mean performance of work unit B. Once again, that's an ideal instance to use a two-sample t-test. Same with geographic regions. If A is Alabama and B is Mississippi, then we could two-sample t-test to then compare whether these bars that look visually different are indeed statistically different or statistically significantly different. We could do a two-sample t-test for that. And then lastly, with, well, I guess that was the last one. So in short, anytime that we would make a bar chart with two bars, then that should set off bells, that should set off alarms in your brain that, hey, I can use a two-sample t-test to indeed see whether these two bars are statistically significantly different in regards to my outcome of interest. Okay. So I know we went through two-sample t-test pretty quickly, but like I said, if you understand one-sample t-test, then a two-sample t-test should be pretty straightforward. Do y'all have any questions about two-sample t-test? Are there any questions whatsoever about a two-sample t-test? Okay, going once, going twice. Okay, I see that there are not any questions, so we are just going to go ahead and move along. I know we're covering a lot, but we have to since we missed that one day, and I apologize for that. Yes, so someone just now asked guides on Matt C. Howard. Yeah, I sent y'all an email. It was right before class started today. Yep, and you have guides. And then, yeah, this is something, I'm glad you brought that up because I do need to note this. So there are guides on mattchoward.com. You can perform a one-sample t-test in both Excel and Jamovi. You can perform a two-sample t-test in both Excel and Jamovi. You can perform, and we're going to cover ANOVA. ANOVA actually has both one-way and two-way ANOVAs. You can do a one-way ANOVA in both Excel and Jamovi. However, a two-way ANOVA, there's a really critical piece of information that Excel will not provide. So for two-way ANOVA, it's preferred to do it in Jamovi. And in fact, on an exam, for instance, if I gave you a question that asked about a two-way ANOVA, then you should use Jamovi, because that key piece of information that Jamovi provides that Excel does not, that could be something I would ask you on a test. So therefore, long story short, yes, guides on mattchoward.com. Yes, I sent it through email. Excel can do one-sample t-test, two-sample t-test, one-way ANOVA really well, whereas Jamovi can do one-sample t-test, two-sample t-test, one-way ANOVA, and two-way ANOVA. So yes, that is correct. Jamovi will cover everything in regards to everything we're covering today, whereas Excel can cover most everything. It just doesn't do quite as well at a two-way ANOVA because it doesn't provide everything you need to know for a two-way ANOVA. So yes, Jamovi covers everything. Yep, that is correct. Okay, any other questions or comments? Okay. So moving on then, so now we're going to cover ANOVA. So we just covered one sample t-test and we just covered two sample t-tests. So now we're going to cover ANOVA. So as we covered at the start of the lecture today, which was only 45 minutes ago, this time is going by really quickly. So at the start of the lecture, we talked about how the things we're covering today is explaining the difference between groups. And we're only going to talk about when our outcome is gauged as a separate measured variable. So we might have something like the difference between groups, the difference between classrooms, and we're comparing their test scores. Our grouping variable in that example was classrooms. We have classrooms as our grouping variable, and our outcome is test scores as our separate measured variable. So what we covered so far is when you have one group, which was a one sample t-test, and when you have two groups, which is a two sample t-test. Sometimes just call it a t-test. So therefore, we've already covered when you have just one group. We already covered when you have two groups. So as you can guess, an ANOVA is going to be when you have more than two groups. When you're trying to compare the difference between groups on a separate measured variable, and you have more than two groups. And this can be when you have 3, when you have 4, when you have 5. Theoretically, it could be if you had 1,000,000 groups. Theoretically, that's not going to happen. However, theoretically, you could perform an ANOVA to compare 1,000,000 groups. So once again, ANOVA is when you're explaining the difference between groups, you have a separate measured variable, and you have more than two groups. You're going to be using an ANOVA in that case. Okay. So I know most of y'all haven't done homework 4 yet. Some of y'all have. If you have, good job. You didn't have to do it this early, but you could have. But as you'll see when you do homework 4, performing multiple t-tests to compare multiple groups is going to be a little bit difficult. That's because on homework 4, I think there's a total of 4 groups. So therefore, if you're performing multiple t-tests to compare multiple groups, you would have to do a t-test on the difference between groups 1 and 2, 1 and 3, 1 and 4, as well as 2 and 3, 2 and 4, and then also 3 and 4. So therefore, if you have 4 groups, and you want to try to do t-tests to compare all those groups, you would have to do more than just 4 t-tests. You actually would have to do 6 t-tests in that example, because you have to compare 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. So therefore, if you have more than 2 groups, performing multiple t-tests can be a little bit difficult, because you have to make each individual group comparison. So therefore, performing separate 2 sample t-tests to compare more than 2 groups is clearly not ideal. It's very cumbersome. It takes a lot of time, it takes a lot of effort, and it takes a lot of analyses. However, there are other concerns. There are other concerns with performing many 2 sample t-tests to compare more than 2 groups. And the main statistical concern with that is it increases your family-wise error rate. Performing multiple t-tests to compare more than 2 groups results in an increased family-wise error rate. So therefore, what is a family-wise error rate? And the answer is when we perform a t-test or any statistical analysis, that shouldn't say most any or any statistical analysis, we typically assume a 5% chance of committing a type 1 error. And that's because we set the alpha of 0.05. So whenever we perform a t-test or any statistical analysis, we typically assume a 5% chance of committing a type 1 error, because we set that ourselves by setting an alpha of 0.05. So therefore, what happens when we perform multiple t-tests? The answer is we have to consider the chance of making that error for each individual analysis. We have to consider the chance of making that 5% chance of a type 1 error for each analysis we conduct. So therefore, if you conduct 2 t-tests, or let me back up a little bit. So therefore, the chance of making a type 1 error for each analysis you perform increases at a rate of 1 minus alpha to the m power, or the number of analyses you're running. So that's the formula you would use to get each of these numbers. So I'm not expecting you to know that formula. This formula will never, ever, ever be on a test. I just want you to know this in the abstract, or know this conceptually, is that if we typically just perform 1 analysis, we assume we have a type 1 error rate of 5%. However, if we're performing 2 analyses, such as 2 t-tests, we would have a type 1 error rate of 9.75%. If we do 3 t-tests, it's closer to 14%. 4 t-tests, it's closer to 19%. 5 t-tests, it's closer to 23%. And then 6 t-tests, it's closer to 26.5%. So in your homework, what you're going to be doing on homework 4 is I'm going to ask you to do t-test comparing all the individual comparisons of 4 different groups. So 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and then 3 and 4. That's a total of 6 t-tests. That would be a total of 6 t-tests to compare all the individual comparisons between 4 groups. So therefore, on homework 4, you didn't have a 5% chance of committing a type 1 error. You instead have a 26.5% chance of committing a type 1 error. And that's called family-wise error rate. Family-wise error rate is the chance of committing a type 1 error among all the analyses you're performing to investigate a certain research question. In this case, your research question is, what's the overall difference among those 4 groups? And you do not have a 5% chance of committing a type 1 error in regards to investigating that research question. You instead have a 26.5% chance of committing a type 1 error when you're comparing all the individual group comparisons of 4 groups, like you do on homework 4. So therefore, that's extremely concerning. Already we established it in class when we talked about confidence intervals, when we talked about p-values. Already we established in class that a 5% chance of committing a type 1 error, that kind of sucks. We deal with it because we have to, because that's how statistics works, but we're petrified of committing a type 1 error. We never want to commit a type 1 error. A type 1 error, if we're performing analyses on medicines, if we're performing analyses on surgical procedures, literally is life and death, literally. So therefore, we are really afraid of committing a type 1 error. We want to minimize that when possible. So that's why we say that a 5% chance of committing a type 1 error is typically the maximum chance we're willing to take. However, if we're performing all these t-tests, like I asked you to do on homework 4, we're not only going above a 5% chance, we're going way above a 5% chance of committing a type 1 error. Because our family-wise error rate is 26.5, that means we're going to have a 26.5% chance of committing a type 1 error rate on homework 4. So that's terrible. That's awful. We should feel real bad about ourselves. If you're a statistician working in a company and you ever think that, hey, I have a 1 in 4 chance of committing a type 1 error, then you should deeply, deeply, deeply think about where you went wrong. You should deeply consider about, hey, what am I doing to this company? Why am I okay with making all these mistakes? Why am I all right with a type 1 error rate that's so incredibly high? You should reflect on that, think about your life choices, and then get back about how you can do your analyses in a different way. And that's what we're going to do with ANOVA. We're going to think about how we can address these concerns. So as you've probably guessed, an ANOVA can help address this family-wise error rate. An ANOVA can help reduce our type 1 error rate when we're performing a lot of different analyses, or when we think we would otherwise have to perform a lot of different analyses, because an ANOVA is just one analysis. An ANOVA can compare all those different groups. So if we have groups 1, 2, 3, and 4, an ANOVA can compare all their means all at once, all with one analysis. So it keeps our type 1 error rate at 5%. So whereas performing multiple t-tests would have a family-wise type 1 error rate of 26.5% when comparing 4 groups, an ANOVA keeps it at 5%. ANOVA keeps it way low. So that's why we always want to use an ANOVA when we have more than 2 groups. That's why we always want to use an ANOVA when we have 3, 4, 5, so on and so on groups, because it keeps our type 1 error rate at 5% when we have more than 2 groups. And then also today we're going to learn about post hoc tests, and that's the thing that Excel will not give you. That's the thing that Excel does not give you. And that's why we need to learn how to use Jamovi when we're doing an ANOVA, because Excel will not give you that. And now that I think of it, I think before I said when I was covering things that Jamovi does and Excel doesn't, I think before I said Excel will also do a one-way ANOVA, and Excel will give you the one-way ANOVA, and in fact it could give you a two-way ANOVA if you ask it to. However, it will not give you these post hoc tests. So in fact, Excel does not adequately perform either type of ANOVA. And that's why we need to learn how to use Jamovi, because Jamovi does perform those post hoc tests, which we do need whenever we're performing either a one-way or a two-way ANOVA. So thank you for asking that question before. Okay, so moving forward. So therefore, what is an ANOVA? The textbook definition is it's used to analyze the differences among groups' means and their associated procedures. My definition, I think, is a little bit easier, is it's used to test whether the means of a measured variable in more than 2 groups are significantly different. So it's used to test whether the means of a measured variable in more than 2 groups are significantly different. And I like this definition because it's pretty straightforward. So whenever you have more than 2 groups, such as 3, 4, and 5, and you want to see whether their means are significantly different, you would then perform an ANOVA. So once again, any instance that you think that you would want to compare means with more than 2 groups, you're going to want to do an ANOVA. Okay, so for example, these are going to be very similar to when we had a 2-sample t-test, where it's going to have more groups. So if there's ever an instance where you think, well, this seems like it should be a 2-sample t-test, but I have more than 2 groups, then you're going to want to use an ANOVA. So for example, some questions you might have that you would use an ANOVA is which class has the highest test scores? Is it Dr. Howard, Dr. Smith, or Dr. Kim? Once again, we're comparing average test score, we're comparing the means, and in this instance, we have three groups, Dr. Howard, Dr. Smith, Dr. Kim, and we have that separate measured outcome of test scores. Oops. The next example is, are people with brown, black, or red hair the tallest? So in this instance, we have a grouping variable of hair color that has three groups, brown, black, or red. And then we have a separate measured outcome variable, which is height. So you can see whether people with different hair colors are statistically significantly different in regards to their average height. The next one is which training group performed the best, the no training group, the old training group, or the new training group. And once again, this would be pretty common in practice. So if you're currently working in HR somewhere, you would use an ANOVA for this one day, where you would have three groups of employees. So employees that receive no training whatsoever, employees that receive the old training, the training that you've been using at your company forever, but then also employees that have the new training. And therefore, you would collect data regarding those three training groups or employees that went through those three trainings, and you could perform an ANOVA to see, are there a significant difference among those groups? Hopefully, you would find, yes, there is, and hopefully you would find that the new training group is doing much better than the other two, but it's also possible you would see that there's no difference. It's also possible your ANOVA would not be statistically significant, and that would insinuate that your old training group and your new training group is no different than a group that didn't do any training whatsoever. So I would suggest that you should just throw your trainings out the window because they're not any better than doing no training at all. Okay. And the last example is which company has the highest employee satisfaction? Walmart, Target, Sears, or JCPenney. And in this example, you could get employees from each company. You can measure their job satisfaction, and you can perform an ANOVA to see whether the average job satisfaction of employees at each of those companies are statistically significantly different. And then this goes a little bit further than what we've covered so far, but then you could perform post hoc tests to see, well, what's the nature of those differences? Is Walmart better than the others? Is Target better than the others? Is Sears better than the others? Or is JCPenney better than the others? Et cetera, so on and so on. Okay. That should say when performing an ANOVA. So that should not say t-test, but instead that should say when performing an ANOVA. There we go. That worked out terribly. So when performing ANOVA. Okay. So that should say when performing an ANOVA, our null and alternative hypotheses are usually, and this is the same as when we did a two-sample t-test. The null is that there's going to be no difference in the means of the groups, and our hypothesis, or the alternative hypothesis, is there is a difference in the means of the groups. So therefore, the null hypothesis is there's no difference. Our hypothesis is there is a difference. So once again, as always, if p is less than 0.05, we can reject the null that there's no difference. If p is less than 0.05, we can reject the null that there's no difference among the groups. And we can go with our hypothesis, or the alternative hypothesis, that there is a difference among those groups. We can go with our hypothesis, or the alternative hypothesis, there is a difference among those groups if p is less than 0.05. Okay. So therefore, we can perform an ANOVA when we have a grouping variable with more than two groups and a separate outcome variable. So we can perform an ANOVA when we have a grouping variable with more than two groups and a separate outcome variable. And I'll give a very quick visual demonstration again, just to make sure that y'all understand how an ANOVA works. As an ANOVA would be used, let's say if we have different groups and we want to compare their means, we might have three different groups and their distributions might look like that. An ANOVA would tell us whether overall, is there a significant difference in the means of these groups? And if it's statistically significant, then yes, there is a difference in the means of those groups. On the other side of the coin, you might have an instance that looks like this, where you have three different samples and their distributions are much closer together. Their variances might be much wider and overlapping. And you could still conduct an ANOVA to see, are the means of these three groups statistically significantly different? And in this instance, it might be the ANOVA is not statistically significant, so you cannot say that there's a meaningful difference in the means of these three groups. Okay, so moving forward, so once again, we can perform an ANOVA when we have a grouping variable with more than two groups and a separate outcome variable. So the example we've been using over and over and over is that if we might have a training group with group A, group B, and group C, then we might want to see whether the performance of the employees in these three different groups significantly differ. So that could give us an inference of whether Those who went through training groups A might be better than B and C, whether B is better than A and C, and whether C is better than A and B. So we can just do an ANOVA to see, is there an overall difference among those groups? Okay. So therefore, let me back up a little bit. So therefore, in this instance, we have one grouping variable. In this instance, we have one grouping variable, and that's training group. So we can perform an ANOVA to see, is there a significant difference among the groups regarding this one grouping variable? Is there a significant difference among the groups regarding this one grouping variable? However, ANOVA can also tell you whether there's a significant difference among multiple grouping variables at the same time. So an ANOVA can also tell you whether there's a significant difference among multiple grouping variables at the same time. And this is called a two-way ANOVA. So what we just looked at on the prior slide, so what we just looked at right here, that's what we would call a one-way ANOVA. When we have one grouping variable, and we're trying to see the difference among the groups for one grouping variable. This is called a one-way ANOVA. However, we can also perform a two-way ANOVA, and a two-way ANOVA would tell you whether there is a significant difference among multiple grouping variables at the same time. And that would be called a two-way ANOVA. That's when we would perform a two-way ANOVA. And as long as you still have a separate outcome variable, you can do that. You can see whether there's a significant difference among multiple grouping variables at the same time, as long as you have a separate outcome variable. So you might have two grouping variables. So let's say we have, well, we'll get that on the next slide, or we'll get to it right here. So for instance, we might have three different training groups, and each training group was applied at three different factories. So in this instance, we have two grouping variables. One grouping variable would be the training. So we have three different training groups. So just like we saw in the last slide, we might have training group A, B, and C. However, we also have three different factories, and that would be our second grouping variable. So we first have training as a grouping variable, training group A, B, and C, but then we also have three different factories, which is a different grouping variable. And we might have factory 1, 2, and 3. And we could perform a two-way ANOVA to see, is there a significant difference among the training groups in regards to performance, but also is there a significant difference in regards to the factories in regards to their performance at the exact same time. We can assess both of these group differences at the exact same time by performing a two-way ANOVA. And hopefully this picture is a visual demonstration that will help you out a little bit. So in this instance, we have our training grouping variable, and we also have a factory grouping variable. We also have a factory grouping variable. So we have a training grouping variable, and we have a factory grouping variable. So we can perform a two-way ANOVA to see, is there a difference among training group A, B, and C? And is there a difference between factory 1, 2, and 3? And we can assess those differences at the same time. So we can perform a two-way ANOVA, and it might tell us that C is significantly different, or let me back up. It could tell us, undo. It could tell us that overall, there is a significant difference between the training groups, and it could also tell us at the same time, there's a significant difference among the factories. So it could tell us both, is there a difference between training group and factories at the same time. For this to occur, we still have to have our separate measured outcome variable. So we would still have to have something like a measurement of performance, but also we would have to have observations for each combination of training group and factory. We would also have to have observations of each combination of training group and factory. So we would have to have participants or individuals that went through training group A, as well as factory 1 or in factory 1. Sorry about that. We would have to have participants that went through training B and also were in factory 1. And we would have to have participants that went through training C and in factory 1 yet again. And then for each other combination, factory 2 training A, factory 2 training B, factory 2 training C, and then factory 3 training A, factory 3 training B, and factory 3 training C. So we'd have to have each combination of training group and each combination of factory. We have to have participants that represent each combination. We would have to measure their performance, and then we could perform a two-way ANOVA to see, is there a significant difference in regards to training group, and is there a significant difference in regards to factory, in regards to performance. We can assess those differences at the same time. Okay, so here is a possible outcome we could get from that. So let's say these are our numerical results. So let's say these are our group means. So looking at these group means, would we expect there to be a significant difference among the means of the factories? So what would we expect there to be a significant difference among the means of the factories? What do y'all think? Any guesses? Would we expect there to be a significant difference among the means of the factories if these were our numerical results? Okay, yeah, so everyone said yes, and you're exactly correct. So good job, give yourself a pat on the back. I'm good to see that you're getting it. That gives me a lot of relief, so thank you for that. Yes, we would expect there to be a mean difference. And it's because every observation in factory 1 had a mean of 10. So whether you went through training group A, whether you went through training group B, whether you went through training group C, as long as you were in factory 1, you had a mean of 10. However, every observation for factory 2 had a mean of 1. So therefore, that would give us very strong support that it's factory 1 that's making a difference, that it's the main determinant is whether you're in factory 1 that determines your performance, because everyone who went through factory 1 had a mean of 10, and then everyone who went through factory 2 or 3 had a mean of 1. Okay, so then based on this, since we're using a two-way ANOVA, we can analyze both of these differences at the same time. Would we expect there to be a significant difference among the groups in regards to their training group? Would we expect there to be a significant difference among the groups in regards to their training group? What do you think about that? Yep, and you are exactly correct. I saw 2 no's incredibly quickly. Good job, very good job. We would not expect there to be a significant difference among training groups. We would not expect there to be a significant difference among training groups because the pattern for the 3 training groups was very similar, and in this case it was identical. If you're in training group A, you had 10, 1, and 1. So therefore, overall, that's an average of, what would that be? An average of 4. Even though this one was a little bit higher, on average, people scored a 4 if you went through training group A. If you went through training group B, that had a similar, in this case, the same pattern. It was a 10, 1, and 1. So overall, people who went through training group B also had an average of 4. And then in training group C, you had a pattern of 10, 1, and 1. So once again, this was an average of 4. So in this case, we see it did not matter what training group you went through. Your scores would be the same. It didn't matter if you were in training group A, B, or C. Your scores were going to be the same. The only thing that influenced what your scores would be whether you're in factory 1 compared to 2 and 3. So therefore, because of that, we would say there's a significant effect of factory, and there was not a significant effect of training group. So once again, significant effect of factory in this example, not a significant effect of training group. Okay, so let's look at another example. So in this example, here are the numbers, 10, 10, 10, and then everything else is a 1. So in this example, would we expect there to be a significant effect of factory? Would we expect there to be a significant effect of factory? Yep, and once again, y'all get it correct, so good job. It is still no, because it doesn't, the patterns across the factories are the exact same, but it was still 10, 1, and 1. So on each of those, the average for the factory was 4. So it didn't matter what factory you're in, this factory still had the same scores across factory. However, for training group, would y'all expect there to be a significant difference among the training groups? What do y'all think about training group? Yep, y'all are exactly correct, so good job. Yes, because it seems like the only thing that makes a difference is whether you're in training group A versus training groups B and C. That's the only thing that makes a difference, because those in A had an average of 10, whereas those in B and C overall had an average of 1. So it only matters whether you're in training group A versus B and C, whereas none of the factories made a difference. None of the factories made a difference. So in this case, if we ran a two-way ANOVA, it would probably tell us there is a statistically significant effect of factory in this example, but not for training group if we ran a two-way ANOVA. And a two-way ANOVA would assess those independently and tell us whether factory is statistically significant, and also tell us whether training group is statistically significant. Okay. One thing y'all should know about that, though, is in this example, we can determine whether the training group has a significant effect and also whether the factory has a statistically significant effect. However, we can also determine whether there's a significant interaction effect. We can also determine whether there's a significant interaction effect. And this is extremely important. We see this all the time in both research and practice. We always need to think about interaction effects because they're so common and they're so influential. So therefore, we need to first figure out what an interaction effect is. And an interaction effect is when the effect of a grouping variable depends on the other. And this is the definition in the context of ANOVA. We're going to cover interaction effects in the context of regression next week, but this is the definition for the context of ANOVA. So in the context of ANOVA, an interaction effect is when the effect of a grouping variable depends on the other grouping variable. When the influence or the effect of a grouping variable depends on the other grouping variable. So what would that look like, or what would that mean? Here's an example of an interaction effect. Here's an example of an interaction effect. So in this example, we might run a two-way ANOVA. It might tell us that the effective training group was significant because those in training group A on average had higher values than B and C. It might also tell us the effective factory is significant because those in 3 had a higher value than 2 and 1. But what's really going on here is there's a significant interaction effect. And if you run a two-way ANOVA, I believe in both regression and for sure in Jamovi, if you run a two-way ANOVA, they'll also give you an estimate of whether you have a statistically significant interaction. And that would look like in most stats programs, including Jamovi, you'll have something in your output that looks like factory times training group, and we'll just abbreviate it here. You'll have something in your output that looks like factory times training group. And that usually is an indicator of whether you have a statistically significant interaction. So Jamovi might give you something like this. It'll give you numerical results, and it might give you 2 asterisks. And that would mean that you have a significant interaction effect. And if you have a significant interaction effect, that means it's this interaction that's driving your results. That kind of like what we talked about before with quadratic regression. This is a completely different concept, but similar practice, I guess you would say, is that if you have a significant interaction effect, that's what you interpret with your two-way ANOVA. That even though it's going to tell you that your, we call these direct effects, even though it's going to tell you your direct effects are also significant, if your interaction is significant, then that's the only thing you interpret. If your interaction is significant, that's the only thing you interpret. And the reason why is because if you have both your direct effects, so both the effect of training group and the effect of factory is significant, but also your interaction is significant, the only reason why these were significant was likely due to your interaction. So once again, if your interaction effect was significant, then the only reason why your direct effects or the effect of training group and factory independently were significant was likely due to the interaction itself. And that's why if we have a significant interaction, that's the only thing we interpret in our results. We don't interpret our direct effects at that point. We would then only interpret our interaction. And once again, we only do that if our interaction is significant. If our interaction is not significant, we would then still interpret these direct effects. So if our interaction is not significant, we would still look at these direct effects, the effect of factory and the effect of training group. It's only when this interaction is significant do we not interpret these. Okay, so anyways, let's look at this result and let's ask ourselves, well, why is this an interaction? Why is this interaction? And as you know, an interaction is when the effect of one grouping variable depends on the other grouping variable. And in this instance, we see that it wasn't necessarily just being in group A that caused the values to be higher. It was this particular combination of being in group A and factory 3. It was this particular combination of being in group A and factory 3, because all the other values in this example were identical. And in practice, you'll never see the values being identical. They're going to be close to similar. But an interaction occurs is when you have one particular combination that's much higher than all the others. When you have one particular combination that's much higher than the others, that's when an interaction occurs, or that's when it often occurs. So in this example, as you see, it was training group A that matched with factory 3, and that was the only instance we had particularly higher values. That's the only time we had particularly higher values. And that indicates there's an interaction because the effect of training group depended on the factory, and the effect of factory depended on the training group. That it wasn't necessarily training group A that had the overall effect. It wasn't necessarily factory 3 that had the overall effect. Instead, it was the combination of training group A and the combination of factory 3 that had the significant overall effect. And we see that a lot in practice. In this example, it might be that this was something like no training, this was something like watching a video, and this was something like having a live presentation. And at factory 1, they had a really bad presenter. At factory 2, they had a really bad presenter. But at factory 3, they had the best presenter you could possibly ever imagine. So therefore, it wasn't necessarily the effect of having a presentation, It was the effect of having this particular presenter. It was the effect of having this particular presenter who then couldn't really do much in the different training methods. However, for this training method, they were able to give it their all, show them what they got, and were able to give a really good training. Okay, so therefore, in short, a two-way ANOVA can tell you whether you have a significant effective factory, whether you have a significant effective training group, but also whether there's an interaction between factory and training group, which would indicate that the effect of one depends on the other. And you see that here with this one combination being significantly higher than all the others. Okay, any questions about that? Any questions about that at all? Any questions whatsoever? Okay, if there's no questions, I think the lecture should last for only about 15 more minutes. So let's go ahead and finish the last 15 minutes, and then I'll leave it open to y'all that y'all can do the guides, and I'll be here for questions. So let's go ahead, power through, and finish the last 15 minutes. Okay, so to conclude the lecture today, you might ask yourself that, all right, we can run a one-way ANOVA or a two-way ANOVA, and it'll tell you whether there's a significant difference between multiple groups, or maybe even that an interaction exists. What else might we need to know, however? So let's keep it simple. Let's say we run a one-way ANOVA, and let's say it tells us there's some type of difference between training group A, training group B, and training group C. So let's say we run that one-way ANOVA. It tells us there's some type of difference between A, B, and C, and an overall ANOVA is statistically significant. There's some type of difference. What else might we want to know about these three groups? Can anyone tell me? So in addition to, is there just an overall difference among these groups, which an ANOVA would tell us there's some type of overall difference, what else might we want to know about those groups in regards to their mean differences? Yeah, okay, I'll take that. So which one performs the best? Yes, exactly, correct, good job. So give yourself a pat on the back. You got that completely correct. You might want to, even though if you know that there's some type of overall difference among these groups, an ANOVA by itself isn't going to tell you which groups actually differ. An ANOVA by itself isn't going to tell you which groups actually differ. Then it will tell you, hey, there's some type of difference between these groups, whether you perform a one-way or a two-way ANOVA. It will tell you that these groups somehow differ, but it will not tell you the exact nature of those differences by itself. An ANOVA by itself will not tell you the exact nature of those differences. And that's why Excel doesn't give you everything you need to know when you perform an ANOVA, because Excel will give you the results of ANOVA, but it doesn't give you this next analysis that we need to understand the differences between these groups. Because when you run an ANOVA, let's say this is our distribution of the groups down here, you could have an instance where A looks like that, B looks like that, and C looks like that. And that would probably be statistically significant, that A is different than B, A is different than C, and B is different than C. We see these are pretty far apart, and they're pretty, their distributions are pretty close together, that there's front to their means. So therefore, there's a significant difference among the groups. So in this case, the ANOVA would probably be significant. However, one thing you should know is that if we ran an ANOVA, this would also be statistically significant. This would also be statistically significant. Then in this instance, there's not a difference between A and B. A and B are really close together and really similar. However, C is all the way out here. C is the thing that's driving this statistically significant ANOVA effect by itself. That A and B don't differ at all. However, your ANOVA might be significant because C is really, really different than A and B. So therefore, we need to figure out what can we do after performing an ANOVA to actually see how our groups differ. Because our ANOVA will just tell us that overall there's some type of difference among these groups, but then we have to do another analysis to see what is the nature of these differences. Is it just C that's driving this effect, or is it A, B, and C overall are just different from each other? Okay. And as you probably guessed before, we perform post hoc tests. So I brought up post hoc tests before, and this is exactly what they're used for. Post hoc tests come after the ANOVA. That's why they're called post hoc tests. and they analyze the difference between all the individual groups. They do all the individual group comparisons. So a post hoc test would compare group A and group B, group A and group C, and group B and group C. So a post hoc test analyzes the difference between all individual groups. And post hoc tests are very similar to t-test. Post hoc tests are very similar to t-test. However, they do differ from t-test because they account for the family-wise error rate. Post hoc tests do account for this family-wise error rate. Compared to a t-test, there's some differences in the way post hoc tests are calculated. We'll talk about that in a slide or two, but just know that post hoc tests are very similar to t-test. Post hoc tests compare two groups. When you run an ANOVA and follow it up with post hoc tests, in Jamovi, and also if you were to use SPSS, SPSS does this too, but in Jamovi, it will give you the post hoc test for each individual group comparison. So we'll compare group A and B, group A and C, and group B and C, but it does account for that family-wise error rate. So even though it's similar to a t-test theoretically, and in practice for that matter, it does differ based on accounting for family-wise error rate. Okay. So things you should know is many different types of post hoc tests exist. I believe it was particularly in the 70s and 80s, there was a time where a lot of statisticians got really into post hoc tests. And there was a time where post hoc test after post hoc test after post hoc test was being invented. I think in Jamovi only gives you 2, maybe 3 different post hoc tests you can perform. If you use SPSS, then there's going to be, maybe a dozen different post hoc tests you can run. At least. I'm not going to make you remember all the post hoc tests. I'm not even going to, so someone already looked it up in Jamovi, and it gives you the games, hows, and 2K. So the games, how, and 2K are the 2 tests. Yeah, and I'll get to that in 1 second. So thank you for typing that into chat, because that will come up in a minute or two. But I'm not going to make you memorize all the different types of post hoc tests. I'm not even going to make you remember their exact differences. I just want you to know that in this class, post hoc tests just generally differ on how liberal or conservative they are, and that has nothing to do with politics. There is nothing political about post hoc tests. All this means is if you have a liberal post hoc test, then there doesn't need to be as much of a difference between the groups for it to be statistically significant. So therefore, if you have a liberal post hoc test, 2 groups that look like this with a little bit of overlap, a liberal post hoc test might find those to be statistically significant. It's more liberal, it's more lenient, that even though there's this overlap right here, a liberal post hoc test might still find it to be statistically significant. On the other hand, a conservative post hoc test might not find it to be statistically significant, So therefore, typically when you do post hoc tests, typically you perform a lot of different post hoc tests that range in how liberal or conservative they are. And as you see, typically when I teach this class, typically we use SPSS. SPSS has the Bonferroni post hoc test, which is very conservative. It has the LSD post hoc test, which is more liberal. And it has the 2Ks post hoc test, which falls in that middle ground. So typically in this class, whenever we run post hoc tests, we actually run 3 different types. And we run one that's conservative, one that's liberal, and one that's in the middle. And we estimate, well, what are our group differences based on overall what do our post hoc tests say? If 2 of them say it's significant, then we might say, all right, that seems like a significant difference. If all 3 do, then definitely has a significant difference. But if only one says it's statistically different, we might still question that. We might just say, well, that might just be because that one test was really liberal. The others that are more moderate and conservative didn't find it to be significant. So we don't know if we would really agree with that. However, for this class, we are not using SPSS. And as someone in the chat already said, there's only 2 analyses that are there's only 2 post hoc tests that Jamovi will run. So therefore, in the context of this class, do I have it on the next slide? Okay, I don't have it on the next slide. In the context of this class, just go with what I put in the guides. So if you're following the guide, off the top of my head, I believe I put 2K, maybe I'm wrong with that. But in the guide, I directly tell you which post hoc tests you should run based on what Jamovi has to offer. So therefore, just go with what the guide says. Jamovi only offers 2. There's one of them that I picked out that I think that works better. So you should just go with that one post hoc test that I recommend in the guides. So instead of doing a lot of different, okay, so I put games how, so I apologize for that. It's not 2K, it's games how. So typically in this class, I would get y'all to run a lot of post hoc tests and look at the overall interpretation. Instead, since Jamovi only offers 2 post hoc tests, I just want you to run the games how and then interpret the results based on that. Interpret the group comparisons based on the games how post hoc tests. So thank you for looking that up. I greatly appreciate that. Okay. One last thing, very last thing about ANOVA and post hoc tests is you must specify whether you want to estimate fixed or random effects. To keep it simple in this class, particularly because this class, once again, is scrunched together due to missing a class, and that's okay. We're just going to assume random effects. So if you're running an ANOVA, you typically have to designate whether you think your effects are going to be fixed or random. In this class, we're just going to assume random effects. And the following slide has more information if you want to know the difference between fixed or random. I'm not going to expect you to know that difference. Instead, we're just going to assume random effects. Once again, if you want to know more about stats, the next slide has it there for you. But for the purposes of this class, for any homework, for any test, we're just going to assume random effects. Okay, and there's the slide with all the information you would need about random effects. If you want to know more, and more information can be found at that website link. It's there in the PowerPoint if you want it. Okay, so are there any closing or concluding questions on ANOVA or post hoc tests? Or 1 sample t-test, 2 sample t-test? This is the end of the lecture. Are there any questions whatsoever about anything? Okay, so apparently on the guide I said 1-way ANOVA, games how, and 2-way ANOVA 2K. Does that matter? That's a good point. I'll go back and double check that. I will certainly go back and double check that. I should probably make those consistent. I don't know why I would have chose one and not the other, or chose one for 1-way and the other for 2-way. I'll go back and double check that. I'm writing a note right now. So double check post hoc. I'll go ahead and check that because this is what you'll do for homework 5. So this is what you'll do for homework 5. So I'll go back and double check that before anyone submits their homework 5 and make sure that I had a reason for that and preferably make it consistent. So very good point. Thank you for that. Okay. Any other questions or comments? Going once, going twice. Okay. So I'm going to go ahead and the lecture's done. Y'all are free to leave if you want to. I'm going to go ahead and turn off my camera. So if you want to go ahead and do the guides, I'll be here that you can type in any question. And as I see questions come up, I'll turn my camera back on and I'll ask any questions whatsoever that you might have. So go ahead, do the guides if you want to. I'm here for questions. I'm here to explain things. Otherwise, you're free to go. Thank you for hanging in there. I hope you enjoyed this lecture. So thank y'all. Yeah, so yes, you can ask a question about homework 3. And also, I think there's a group or 2 I'm supposed to be meeting with. So if you're in that group, send me a message and let me know whether I'm actually meeting with the group or not. So, but yeah, however you want to ask the question, you can ask it in the chat and I'll answer it here. Or we can make a breakout room if you want to ask it privately. Or you can send me, I think in the chat function, you can send a private message if you're okay with me answering that question to everyone. Just let me know what you would prefer.
Hey, so I was the one that emailed you about possibly a meeting after class about something that I had a question with on this homework 3.
Okay.
And me and another classmate met yesterday about it. Is there any way that we could have a breakout room just so we don't give anything away?
Yeah, that's perfectly fine. So I'm going to start a breakout room. So those who are in the main room right now, I'll come back to this main room after I'm done answering this question. So
okay, it's me and Diana Nichols as well. Both
okay.
of us are together.
So one room. Okay, so it is. You are Lexi.
Yes.
Diana Nichols, Lexi. Okay, so I just now opened the rooms. You should have gotten an invite, I think.
Yes,
so
I got it. Okay.
Yep.
Perfect.